Okay, to people who are joining this, this is a slightly different kind of discussion. We are talking about
recording in progress.
A direction, something that I consider to be a major direction in terms of language design. And we have a whole bunch of people here who I hope can contribute in one way or another to the things that we're thinking about. So I just posted this post yesterday about what I've been calling multi-computation. And here's the basic idea. As it's relevant to our language design. What we mostly do in, how does Wolfram language fundamentally work? Well, it's making transformations for expressions based on patterns. And what we're doing is our evaluator takes the first instance that matches, uses that, and keeps iterating until you reach a fixed point. Clearly, that approach, so most of the time, it's sufficient to just know, we're just interested in what the answer is. Okay, the whole idea of multi-computation is this notion that there are multiple, in principle, any given computation, there are multiple things that can be done in that computation. And that we can therefore, and that even knowing knowing what the answer is non-trivial. Now, I think this model of computation, this idea that there are many paths to follow, is something that implicitly is used in many different areas. For example, it's used even in the evaluation of most recursive functions, like a Fibonacci or something like that. You're following multiple paths, and in that case, you're aggregating all of the leaves. Or another thing you might be doing is doing a search problem where you say, I just want one answer, and you want to find one leaf that satisfies some properties. Or you might be doing theorem proving, where you want to find one path that corresponds to a proof. Or you might want to do any of the kinds of things that sort of logic programming brought to one. One of the points of this this post is making the point that there are a bunch of models that one can imagine making that are sort of inspired by a physics project, that for which the question of what the answer is something essentially determined by an observer who is somehow, for example, making reference frames. What is a reference frame? It's something which defines equivalence classes of things here. So we might say this, someplace up here, we had some pictures of kind of reference frames in which we said that, for example, the simultaneous elements at this time step will be considered to be these or whatever else. And so in a sense, we're taking this multi-way collection of this sort of multi-way computation, we're equivalencing things together and saying that's the answer, so to speak. Okay, so what does this mean concretely? So what I've sort of been interested in is how can we, where's a good example? How can we, what's the right model of computation in our environment for something like this? And so again, in our traditional way of doing things, we're just doing, we're effectively doing a nest list of a replace, blah, 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 or actually ultimately we're doing a fixed point of a replace of blah, blah, blah. Okay. What we're saying here is that what we want to be doing is something like a nest list of a replace list, which in other words, we're doing all possible replacements, and then what happens. But I think the most general, a fairly general thing is to imagine that we have a list of expressions and that we're doing, let's say, f of A, g of B, f of C, g of D, f of C, let's say g of C, whatever else. And that what we're doing is something more like a subset replace on these, which takes some set of these things, let's say g of blank, comma, g of blank, let's say g of x blank, g of y blank, I don't know what it might do. That might turn into the splice, let's say, of, let's say f of x g of x plus y, let's say, right? And this, so that would, oh my gosh, that's what I get for having some random thing defined in this session. Okay, so there we go. So, okay, but so this is, so the concept is, I mean, this is kind of these things here we're thinking about, they're like expressions, or they could be thought of as like tokens. And then there are these events, which are the rewriting rules that update to another, to something else. And the point is that in doing this kind of computation, we have to trace a lot more than we do in ordinary computation. It matters how you get to a particular state. We have a bunch of use cases. Okay, where do we need to let's see. I think I had a thing here. Let me just see. Sorry. Okay, so what I'm trying to understand is what okay, let's imagine that we wanted to take our theorem proving system and think about it in these terms. Clearly, there's a more efficient, given that we're only trying to find one path, there's more efficient things we can do than to tree out all these possibilities. But so among the things that we're thinking about is how to represent a path, an evaluation path, what to do with its tentacles, so to speak. And by tentacles, I mean when we're doing, for example, in find equational proof, which is after all doing something very similar to this. I don't know if this is all making sense. And maybe so I mean, find equational proof might have would eventually have a proof graph that looks like this, let's say. And that proof graph is something very similar to what I'm looking at over here. Does that make sense to people? Although typically in this proof, what we've got is, two expressions are coming in, one expression is coming out. And the event is the application of some kind of substitution process that uses a lemma inside a theorem, for example. Does that make sense? This is one example of sort of this model of computation where you've got expressions and events and so on. And the whole this and so that's that kind of case. In the case of chemistry, we've got at the level of a chemical reaction network, we've got the same kind of thing. We've got chemicals coming in, we've got some reaction event, and we've got chemicals coming out. You might also think about that at a lower level in terms of individual molecules, but you could think about that at the kind of overall reaction level. Now, one thing to say is that given this kind of setup where you have these, whatever they are, tokens or expressions, you can imagine, okay, so this particular thing is a single path of history. This is like the replace version. This is a replace list version, and then a thing we can do is we can imagine deduplicating this so that there's only one instance of every, every token occurs only once, and then that's something more like a Petri net, and I'm not sure that that's we could imagine, okay, in our evaluator, we really don't care whether things occur. All we care about is, did it reach a fixed point? We ultimately care about, does it just cycle? I mean, in our evaluator, obviously we have things like the x equals x plus 1 case, where we won't get a fixed point. And we have, in all these years, we've never really found a need to represent the evaluation chain that's going on here. It's just like, well, it didn't terminate, but we don't have, there's not a, we're not representing that evaluation chain. We're just saying it didn't terminate. So, I mean, I think, okay, so that's the basic setup. And I guess that the, There's a question on a live stream already about universal clocks. No, the whole idea of these systems is there is no universal clock. And the whole idea is that you're defining reference frames that, in the case of the interpretation of physics, you're defining reference frames that tell you what events should be considered simultaneous and so on. Okay, was this at least a rough introduction? Was this, I mean, what I'm trying to do is I'm trying to figure out what are the core functions. Is this a general enough concept here to just have these kind of collections of expressions? I don't think it quite is. Okay, so here's an issue. In a picture like this, where you're just saying replace these things, where you have these tokens are interacting in this event, producing other tokens, that is not a particularly good match with something like a string multi-way system. So for example, here we might have somewhere here, we might have a string multi-way system. So what's going on here? This is saying A goes to BBB, BB goes to A. The problem is that the token that is BB is not, that token is mixed up inside this expression that we've got here. And in the case of our hypergraphs and physics, what's happening is that we represent we are knitting together certain tokens to say those tokens correspond to a state. And the tokens are the things that get to be consumed in an event, but those tokens get knitted together to constitute a state. And so in a sense, we've got several levels of knitting things together. We've got knitting together tokens to make a state, and we potentially got knitting together states to make some kind of reference frame type thing where we're saying, you know, across all these possible paths, these are the ones that we consider will happen. So, I mean, another issue is what, you know, as we start thinking about this kind of more fragmented, lower level version of computation, how do we knit together, you know, how do we knit together things into states, or how do we take states and break them apart to do, you know, to be consumed in events? And one place where we've looked at this, we've got a design for this, which I consider to be a little bit overcomplicated, is in the multi-way system function in the function repository. So if I look at that, this is, okay, so here's multi-way system, and it has a ridiculous number of possible things that it looks at here. And, you know, just to give some indication, I mean, there are these states graphs, which are things like this. This doesn't really have a token. I don't think this is a token version, does it? No, it doesn't have a token version. This has a causal graph version, where the causal graph is giving the causal relationships between different updating events. It's saying, you know, which event, the input to which event has to exist for that event. What is the relationship such that one event is causally dependent on another if the input to the first event requires output from the second event? And then we can draw the graph that is the causal graph that represents these things. And okay, so that's the basic.
To what extent are those actually distinct, or are those? I mean, because I see, like, I mean, a lot of them are things like all events branch yield graph and all events branch yield graph structure, which I assume just means it doesn't have vertex labels or something like that.
Yeah, exactly.
Is the actual number of base graphs, you know, aside from these sort of options, is it like 4 or 5, or is it actually like 50?
No, it is. Okay, so let's enumerate them. But I think it plays a little differently when you've already tokenized the things. This is at the states level. One is the states graph, you know, the what states map to what states. Then there's the bipartite, so to speak, annotated states plus events graph. Then the other sort of, then there's the pure causal graph, which is take, let's see, I guess you can derive it. No, you have to say separately from this, you have to say what is the causal dependence of one event on another. In these graphs, in the case of the token event graphs, those things are bundled together. But in this case, you have to separately decide what that causal dependence is. Then the only other, well, a qualitatively different kind of graph is a branch yield graph, which is a graph from a foliation of this graph where you're slicing across and you're asking, what are the ancestral relationships between states in that case. So I think those are the main things. And I mean, this has a lot of extra hair because it's asking for things like it's doing a lot of stuff about effectively confluence checking and causal invariance checking, where it's saying, and that's another important point, is, I mean, so again, well, let me just bring up one other thing here. So just as an example of kind of how this evaluation process works in a more complicated case, in the case of, let me give you an example where our evaluator fails, okay? And that's combinators. So the issue with combinators is, first of all, sometimes combinators, well, here, let's find a multi-way graph for combinators. Let me just find it. Okay, so reminder, combinators are these rewrite rules for expressions, right? And you have a complicated expression, and there are often many places where the expression can be rewritten. This is that expression, and these dark red squares represent subtrees that can be rewritten according to the combinator rules. And the whole point is that one ends up getting this multi-way graph of possible rewrites. And then what can happen is with combinators is combinators have this confluence property that if it's going to terminate, then you always get the same result. So even though there are many different paths which we cannot parameterize, in our evaluation scheme, we are, if we just use /dot to apply the transformation rules for combinators, we're going to go down a particular path here. And we don't have any good way to parameterize what the evaluation order basically is. And in general, okay, I'm going to say, but in the case of combinators, they have this confluence Church-Russell property that if it's going to terminate, it will always terminate in the same thing. It doesn't necessarily have to terminate. And we can find examples here. That's probably an example where, is that an example? I don't know. This is probably an example where some paths terminate, but many paths do not terminate. And we have no way to parameterize that. And we have no way, and that's, we could imagine that this combinator thing, it could be a search problem, it could be, we're trying to fill out a tiling, we're trying to fill out a game tree, these kinds of things. And there might be a terminating case and there might be non-terminating cases, and we don't have a good way to parameterize which of those cases we're going to follow, which is to say, conceptually, we can make the whole multi-way graph, and then we could say we can slice it down, and that's well, I don't know, that's really the kind of thing these properties are doing, but that's the kind of thing we can imagine doing. Now, just to give a sense here, in the theory, in the case of combinators, where we're basically doing transformation rules on expressions, there are certain conventional orderings that we can use that are these kinds of things. These are basically part numbers in the tree, and we're asking in what order, which part number do we replace first? Okay, and so and that could be thought of as, in this multi-way graph, that's effectively defining one of the possible ways we can observe a multi-way graph is by picking a path, and one way we can pick a path is by defining it in terms of what transformations should occur, if that made sense. And to give a sense here, yeah, I mean, so this is something where in the way of thinking about things in terms of multi-way graphs, where we've got states, these are ways in which we're taking states apart. Where is it? How does that work? Let's see. I thought we had a thing. Well, these are state rendering functions, but I thought we had a way to define. Oh, I guess it's in the internal code. How we take a state or an event apart into effectively tokens. So, Max has a somewhat cleaner. Well, I don't like I mean, he has code that is dealing with these pure token event graphs. Wherever I had that. So this is a token event graph where, again, the states are made up by knitting together certain tokens. They could be, so whereas, in one view of things. So in the case of combinators, the knitting together of tokens is a pretty complicated matter, because what you've got is not, even in a string, you've got, one part of the string which may overlap with another part of the string, and those both may be thought of as tokens. I'm not quite sure how to think about that. In a combinator, it's much worse because it's a tree structure, and these quotes tokens are all interwoven because they're subtrees of each other. I don't know, did anybody, like Max, do you have a comment on how to think about tokens from strings?
Well, I mean, they're key characters. So one kind of simple way to think about them is you can emulate a string system with a multi-set system in a pretty straightforward way, because you just have labels for, so characters are tokens, they have labels for different characters. And then you join the neighboring ones.
Right.
Once you represent it as a multi-set substitution system, you can do token event graphs as like in a normal way.
Right, but then what you're doing is you're saying there is a character, it's an A, and it's a position, N, and it is.
No, you don't say it's a position N. You're saying there is this character on the left and this character.
Yeah, okay,
on the
fine.
right.
It's a linked list. It's a linked list with IDs, basically joining the characters.
Exactly.
So, okay, so to ask other people. So first question is, are there analogies people can think of essentially what I would like us to be able to do, let's take logic programming as an example, right? Can somebody say, what would be the kind of, well, let's imagine that you're trying to, I don't know, do tic-tac-toe or something, and you're asking the question, is there a winning strategy for tic-tac-toe? Or you're trying to do the 8 queens problem, which seems to be a very favorite one. In our language, what would we want to be able to specify, and how would we want to be able to specify, get to the answer for this? Anybody want to comment on that? Maybe you could say, Carlo, maybe you could say something about what you've thought about with respect to logic programming in the past.
Okay, first I wanted to say something that about the strategy in which you follow the path. And I think that, in some cases, if it's probabilistic, then basically you're doing Monte Carlo sampling of this space. And
yes,
you can think of, and I think there's a nice connection to probabilistic programming here.
There is.
Yeah. With respect to logic programming, in general, you can define goals. So what you want to do is like you're trying to find it's in a sense it's a lot like theorem proving. You say I want to see if this expression is a theorem in the system, and often what you want to do is say this is a thing I know to be true. Show me, or I want to check whether it's true or not. And these are the axioms of my system, and the axioms might be Joe is Peter's father, and Peter is Jack's father, and you want to know who's a grandparent of who. So sometimes it's fill the blank with all possible things, and sometimes is you just give a complete statement. So Jack is the grandson of, I don't remember the names I said, but and you want to know whether it's true or false. It's other ones you want to list all the grandchildren, for example.
Right. I mean, so one model of that is something like this find replace path function that I had written a version of. So find replace path is basically, rather than generating the full multi-way graph and then just seeing is there, because you could generate the multi-way path and then say find path. Or you can say, this is a sort of dynamic thing where you've given a bunch of replacement rules, A arrow B, C arrow D or whatever, and then you're asked, is there a path from X to Y? And if so, either show, just either your question, is there a path, or show me the path. Does that make sense? I mean, is that's sort of a basic logic programming
operation. Yeah, but even more interesting, sometimes Y has a blank in it, and you want to know all the possible things that can be that blank. And in a sense, there is a nice connection here to graph databases, because that's what they're doing. You're filling blanks and you're trying to build a graph that can lead to those, and you then list all possible solutions.
All right, let's ask Tony then. What how does this resonate with our sort of Sparkle query stuff?
Good question. I'm not sure if I can immediately answer.
Because that's again a case where what you're doing, a very common thing in the Sparkle query case is find an intermediate on a path. Right. So in other words, you're saying, what's a good example? Hey, how do I get up the documentation for
like think about an org chart of a person, of a company. You can ask for all the persons who are directly or indirectly managed by someone. That would be a Sparkle query that you can write. It's kind of complicated in SQL.
Right.
And
so
that's basically, yeah.
Right. So what you're doing, let's see, Sparkle select, I would think would be the type of thing. So in an RDF triple store, is defining a bunch of what is the triple in the triple store? Go ahead.
It's basically a labeled graph. So with our recent Wolfram language release, we got a third argument into the directed and undirected edges, and that's basically a way to represent those triples in RDF stores.
I see. So an RDF triple, and that's, by the way, is something which is like a tagged edge.
Yes.
Yeah, but in this case, they act as tokens, because you can, when you have a triple, you can also ask, what is the relation that links these two things? So, for example, you have Stanley Kubrick and Shining, and the answer is director. That's also something you can do pattern matching on.
Okay, so look, there's a question of relation versus events. What we're calling events here, I think, are, so I would claim that in a triple store, that what you have is something of the form, basically X arrow relator arrow Y, or relation, or whatever you call it. That effectively that's what it's like. One of these graphs, maybe, I'm not sure. Yes, it's like you can think of the triple store as being like, if the events are relations, this is what the triple store is. Isn't that right? This is like a triple store.
I'm not sure. I would say that a triple is, it's not even. There are, in a triple store, you're doing all the possible transformation. Like, these are the tokens, I think. So when you're exploring the thing and getting all the possible answers, you're usually doing a depth first search or something like that, and then you get a table out.
Well, is it wrong if I were to draw a triple store? If I were to make a picture of a triple store, would it look like this? In other words,
no,
I
it's
could
a
say,
state. It's essentially a hypergraph.
Yeah, but what I'm saying is that when you prefer queries are the transformations on the triple store. So in the sense of our multi computing thing, you can say, okay, just do a depth first search and return the first result, or do an extended search and return all of the results. But those are the those are the steps of the evaluation, right?
I see. So what Max is saying is a triple store is a hypergraph in which with ternary hyperedges. Is that correct?
Right. I don't see relation needs to be any different from X and Y. It's just another object.
Yes, fair enough. Okay, so it's just
No,
X.
no, it's not, because it allows for reflection that way.
What do you mean?
Like, usually statements where relation is in the position of X or Y are basically the scheme of the database. So they're telling you what relations are. So it's a form of reflection.
Say that again. So you're
what I'm saying is that you can say something about director in that you want X to be a person and Y to be a movie, and that thing is a statement about the relations.
So there could be a schema.
Yeah, that's the schema are statements where relations appear as X and Y.
Okay.
Yeah, but if you don't focus on just the Sparkle standard itself, what stops us from storing relations as objects of type relation in the same place? So that schema is part of the database.
Yeah, schema is part of the database.
Yeah, but what you're saying is, go ahead.
No, I mean, the only reason it's usually different from the rest is like it's permissions, it's the fact that you want to change it less often.
That's way detailed. I mean, so now let's talk about a query on this. You're claiming that the state of the triple store is a hypergraph, but the query is something outside of the triple store, right? You give a result. It's not transforming the triple store. Is that true?
Some queries do transform a triple store if you're updating or inserting data or deleting.
Okay, but that's a rather trivial thing. That's not something where we've got transformations of the kind that we're thinking about here. I mean, that's different. Okay, but answering.
Well, why wouldn't we? Couldn't we, in principle, make a query that would, for any group of triples, make another triple?
We could, but it's not what you usually do. And I mean, in terms of this, the difference between find replace path and finding an answer from a Sparkle query, if I'm not mistaken, finding an answer in a Sparkle query is a pure find path operation. That is, the triple store is sitting right there, and all the query does is to try and find a path in the triple store. Is that a fair statement?
Yeah, usually more than one.
A path or a subgraph. Yeah.
When does it find a subgraph?
For instance, you can request for all persons their birth date and birthplace. Yeah.
I see. Okay, all right. So that may not be so directly relevant. Okay, let's turn. Maybe we can turn to a different thing, which is, okay, two things that have come up recently. We've got proof representations and we've got chemical reactions, which are both. So let's talk about proof representation. Now, what does it look like when you are, we've got our proof object thing, and our proof object is, where's a good example here? Here, let's pick up a random proof object. So this proof object, right now, we have certain properties of this proof object. So we can say, let's say the proof graph, that's a summary of the proof object. So again, I view that, I think, if I'm not mistaken, this is very similar. I mean, these are, each of those are axioms. Two axioms. I guess we're not showing the laws of inference here, right? Two axioms derive that lemma. And in this case, that lemma, that axiom derived this other lemma. How can there be, why are there two, does somebody know why are there two outputs from that substitution lemma there? Is it just, I see, it's just because it happens to be used in, I'm a little confused by this.
Maybe one is a causal edge?
Yeah, I think it is. I think that's what it has to be.
So there's a difference between normal lemmas and critical pair lemmas, which are triangles. The others are the circles.
Right.
So they are obtained in slightly different ways.
Okay, but this is showing in some combination of states, of token event and some combination of causal graph here. But, again, we can drill into this and we can say, proof data set, and now we've got some representation of, what is this doing? This is saying, we've got, let's see, we've got this lemma, and then the proof, what the heck's going on here? Right, the proof is.
So this is information of how we got to this lemma from previous lemmas or axioms.
Right, but effectively what it's doing is it's defining in the thing that I had above, the simplified thing that I had above here, it is basically this type of operation. It's saying what actually happened. How did we instantiate that law of inference? Is that correct?
Yes, for a simpler inference of the circles, the normal lemmas, that's correct. The critical pair lemmas are a bit more complicated because you have to unify the two previous statements, etc.
Right, but fundamentally, we are, the proof shows how we instantiate laws of inference. So Roger, you had a is Roger with us? Maybe Roger is not with us. Is Roger with us? No, apparently not. Okay. Well, we probably can't represent him. We just were looking at proofs, other situations in which we have proofs. I mean, okay, let's look at simplify. Okay, so simplify, of potential proofs. So simplify as an example, right? So simplify does something very much like all these multi-way graphs, et cetera, et cetera, et cetera. Right now, simplify, we just give the answer. We don't give the path. How should we think about giving the path?
The path or the graph?
Well, the graph is, we're not really constructing the whole graph. I mean, just like in theorem proving, the full multi-way graph, we're absolutely not constructing. Right, the full multi-way graph is quite complicated. I mean, for example, I made some recently. Let's see if I can show you. Let's see. Let me just show you. Actually, I'm just I had done. Okay, these are for Boolean algebra. So these are possible transformations for an expression in Boolean algebra, right? And every one of these arrows, these are equivalent expressions. But the question of what, proving a particular expression is, I've forgotten what this one is, but this is proving a particular expression is just finding a path through this graph of all possible transformations, all possible equivalences. That makes sense. Did that make sense? You were saying,
that's one. So that's the kind of proof where you have a path between equivalent expressions, whereas the proof in find equational proof in general is not a path; it's a graph where you're combining together lemmas.
Look, the only difference is, in one case is a sort of forward multi-way graph, and the other case is this 2 goes to 1. Let's say you're using modus ponens or something. You've got two expressions, and they are combined by modus ponens to give one expression.
But that's a detail. I think we're mixing up, like, the proof graph, like, that's only about how you tokenize and put back together things. Otherwise, it's like operating on the whole state.
I'm not sure I understand that. I mean, I to give an example, like I had, okay, so this is sort of quintessential example of the thing that Ian was mentioning. This is a proof based on, here are a bunch of equivalences, apply those equivalences. This is like one path in a string rewrite system. That's one type of way of presenting a proof. The other type of way of presenting a proof is where you say, is more like what find equational proof does, where you're saying feed in a bunch of theorems, and your goal is to derive true from those theorems, or alternatively to start from true and derive a particular theorem.
Yeah, but what I was saying is that let's say this is applying functions repeatedly. The arity of the function doesn't really matter here when you construct a graph. So, or here with strings, the fact that the pieces you pick have to be contiguous is still only a detail of the tokenization.
Yes, but it may be very important for the language design. I mean, it may be incomprehensible what's going on without that.
Yeah, what I'm saying is that when you look at the whole graph, they should all look the same, like just an arrow. Doesn't matter that you took two parts from different places. That's the universe you're modifying every time you're modifying the global state.
Okay, but look.
Oh, but that might be very, inefficient though, right? I mean, if I understand what you're saying, I mean, you could also say this for the fine equational proof, where it's like, well, you never need to use two separate pieces of information and combine them to
No,
form a
I'm not
third,
talking about
because
implementation, Christopher. I'm not talking about implementation. I'm talking about
cool.
the way you think about, like the way you represent the graph, all these things. If you want a unified theory, shouldn't matter on the arity of the function or on the tokenization.
I agree. Yeah. So I think that this
tokens to events, so the tokens and events to other tokens.
Okay, the issue is this: we have the notion of tokens, we have the notion that we have tokens, we have states, we have events, we have reference frames, and arguably we have goals. Okay, tokens are consumed in events. States are knittings together of tokens. I don't know whether there's an analogous kind of thing for events. Generally, we have thought about events as being just one-shot things. I suppose that the knitting together of events is partly a reference frames kind of thing.
The events are different. In the global multiway system, events take states as input and output, whereas in local ones, they take tokens.
So, sorry, say it again.
So in the local multiway system, events operate on tokens. In the global multiway system, they operate on states. So the events themselves are different.
Well, an event...
They have more information in them in the global multiway system, which means, for example, for one event in the local multiway system, there might be multiple events that correspond to that in the global one.
Yes, but look, in a global multiway system, that is where you are operating on states. So a state might be a complete string, right? You have to have information about where did the event bite into the string and so on. Whereas in a local multiway system or a token event type setup, all you need to know is you take this piece of a linked list, actually just these. Yeah, it is in fact a piece of a linked list because it has the wherewithal to insist that they're contiguous elements, and then you're replacing it by something. I don't quite understand in terms of the generality of this. I don't understand how, for example, combinators and nested tree-like objects work in that respect. Anybody understand that in terms of the? But I mean, this is to me.
Well, you need up propagation events, and it works similarly.
Okay, but so
the problem is, like, if you think in terms of implementation, you cannot just change a sub-expression without also affecting the super expression. So if there is data modification necessary, then it cannot be just one event.
Okay, so strings require linked lists. Are effectively linked lists. Expressions require essentially backfilling events.
So here's the way to think about it. In order to do in order to change a sub-expression, it requires O of log n operations, and that's why it cannot be a single event. If we find another representation of expression which doesn't require that, then we could represent it with one event.
So why does it require O of log n? Because you have to backfill events
because it
to
changes
re-knit.
Super expressions too.
I see, to re-knit the results into the super expression. So that isn't happening in the case of linked lists. You could have another event that reconnects the tokens back into the linked list, but we don't happen to need that.
Well, I
Could
don't
have a
know what does
reconnect.
it mean,
Well, you could imagine
because I know
something.
super expressions.
No, I understand that, but you could have a order one event that is simply it replaces the tokens by other tokens, and then it has to reconnect the replaced tokens back into the original string. I kind of suspect there are cases in biology where that actually happens.
I mean, you can even construct the system such that it constructs states, as part of the updating. And then, of course, when you change the string, you have to construct the new states, which would look kind of similar to expressions. But it's not necessary for strings.
Right. Okay, so let's take another example here. Let's talk about chemical reactions. Okay. Can the people who've been working on chemical reactions say something about how does this, what is a chemical reaction? It's some kind of transformation on a graph that represents a chemical.
In effect, that's what it is, or two graphs that get combined to form one or more new graphs. And depending on the complexity of the total system of all the molecules you're considering and the events, the reactions on them, you can form a multi-way graph over that.
Right.
And you can think of doing a multi-way computation that basically traces out different paths in that graph.
Okay, so the states are full chemical graphs, but the tokens are probably something related to bonds or something. Is that right? I mean, when you
you could think of it that way, that the tokens are bonds that get moved around among a static collection of atoms, so that you're not creating or annihilating any mass.
Mm-hmm.
That's the way I like to think about it. And the events or the transformations are just rearranging the bonds according to the rules of chemical valence.
But so in a typical, let's say, to just pull up some random website, a list of name reactions. Can you pick a favorite name reaction here? Should we do Fischer Indele, whatever the heck that is?
I don't know that one. It's been a few years since I've been in the lab, but
Diels-Alder
let's take something.
Say that again.
Diels-Alder?
Diels-Alder, yes. That's classic.
Diels-Alder.
Third one.
Okay.
Diels-Alder, yes, that's a good one there.
Classic.
Okay, so now let's just understand what on earth is this? This is
okay.
So
it's taking a four atom molecule on the left that has double bonds at the beginning and the end, and a 2-atom molecule on the right that is a double bond, and it's forming a ring out of them, a 6-membered ring, where the 2 new bonds that are used to make the ring come from 2 of the double bonds in the original structure, and the 3rd double bond actually migrates.
All right, so one thing they haven't done here is put labels on this. So in a sense, they should have labeled these things, right?
Yes, but in organic
computationally, yes. For a computational problem, yes.
Okay, sorry. So again, you were.
I was just going to say that a lot of information in chemistry gets elided, and here the notation allows you to elide the C's at each of the vertexes in that graph that's underneath your cursor.
Mm-hmm. I see, but why? How would I know that this thing didn't sort of flip itself over when I got to here? Is that just a convention of the way these graphs are drawn and so on?
More or less. The diagram in the middle of the page on the right shows the mechanism of the reaction as we understand it, and you can go from the left to the middle to the right and see that the atoms have not been rearranged at all. It's just that the bonds are moving.
Okay.
And this type of reaction is very often used where the individual parts are in much larger molecules, not just the simple butadiene and ethylene example here. And those extra pieces of the molecules that in effect form a labeling on the 6 atoms that are involved in the reaction. And those would move along with the atoms to which they're attached. Yeah, here's some examples here.
But this is another horrifying thing because this is stereochemistry, where this is beyond graph rewriting. Is that a true statement?
Yes, you have to take into account 3D geometry if you, yeah. And there are two different ways this type of reaction could go, whether it's catalyzed by light or by heat.
Yeah.
Okay, great. Okay, we're descending into
the minutia. Yes. Well, you asked a chemist a
question. No, I understand. But from our conceptual point of view, in the end, a path in a theorem, the theorem proving path, the theorem proof is going to look very much like this. Is like a proof, something like this. Is that a fair statement? I mean, this sequence of steps.
Yes, it could be a part of a proof. Yes, and where the proof would go from the very beginning of the reaction scheme all the way to the end over a multi-step reaction.
Right, and where Jose was saying we do unification, isn't that, what is the analog of that in chemistry? The unification operation. Go ahead.
That I'm not sure of. I haven't thought about that. The unification would be something like a for all or there exists.
Well, no, it's a question of you've got two pattern expressions and you want to know how does one pattern expression, well, I guess one version of it is how does a pattern expression read on another pattern expression? Is that a fair way to characterize it, Jose?
I think so. Yes, it's fundamentally comparing different patterns. Yes.
Right, but so one of the issues is, tokens could contain patterns, maybe. In which case, then one has to do pattern unification to apply an event to a token.
Mm-hmm.
Okay, what are some other examples? I mean, another one. For example, let's take the case of game graphs. What in that case, one is just saying, here are the moves. I mean, that's here are the moves of the game, and can you get from here to there? Although in the case of games, you might want something more like the branch shield graph, where you're asking, this is a possible state of the game. How do you score different configurations of the game? What about the tiling problem that Max was looking at, a tiling problem? And can you say how that can be thought of as a multi-way graph? How would you do this?
It's not even running.
You mean like the sliding puzzle type of tiling problem?
Well,
I used to think of it in that way in the very beginning, that I think it's pretty far from it, because it's not a process. It's more of a SAT problem.
No, but you can think of it as a process. You're adding tiles.
Well, you can think about a solution of an SAT problem as a process. Sure, because any algorithm, you can think of it.
No, I know that, but I mean, okay, so let's take another example, pure recursion. Okay, so like Fibonacci recursion. The difference between a recursion, evaluating Fibonacci, is you're collecting all the leaves. You want to collect all the leaves, which I claim is not really that different than a search problem. The analog of that, a search analog would be you want to pick a single leaf. Do you agree with that? I mean, in one case, it's really the same type of thing. You're computing, in the case of Fibonacci, you can think of yourself as computing a multi-way graph, where essentially what you've got is nest graph. Let's see what it is. I mean, it's basically nest graph X goes to if X, oops, I have the wrong thing there. If X is less than 2, then 1, else, no, then just a singleton 1, right? Else X minus 1, X minus 2, if I'm not mistaken. And I want that starting at, let's say, 6 for 10 steps, let's say. Am I going to get something crazy? Okay, so I claim okay, this is kind of interesting. This is a token deduplicated version of the Fibonacci, right? Of a Fibonacci evaluation.
Yeah, that's a token graph. I mean, it doesn't show events. Where events take one input and one output.
I put
So
the
token event graph is a generalization of this.
Okay, so Ian put a version of this with tree. Is this going to be the undeduplicated version?
Yeah.
Yes. Sorry, say what were you saying, Max?
So this, first of all, I mean, it's obviously token graph, not a token event graph, because it doesn't show events.
Right.
But other than that, it's just like a token event graph where events have one input and one output.
Okay. No, what I don't understand. Oh, yes, I see what you're saying. I see what you're saying. So this will be two events here, going from 5 to 4 and 3. Those are two different events, right?
Yeah. Yeah, which
Okay.
makes it a kind of a global multi-way system, essentially.
Right. Although we could get a more local version of this if instead of looking at a scalar Fibonacci with single integers, we were to look at lists here. Okay. So this is now the full tree. And what we're saying is this is one way of exploring the multi-way system. So this is a way in which, how do we think about this? I mean, the token deduplication is kind of like an observer type thing. You're making equivalence classes of things. Oh boy, I don't know quite how to think about that. Now, I was going to bring up one other example. Actually, this is a Christopher example. Let's see if I can find it. Navigating somebody else's. Look at this. Let's see if I can bring this up. This is a Christopher example of a puzzle, right? This
isn't token deduplication here memoization in some sense?
Yes, it is.
Yeah.
So Christopher, can you say this is an example, right? This is a sliding block puzzle which has certain moves.
Sure. Yeah.
And the object that you get, I believe, we could call a multi-way graph.
Yes, probably. Although I'm not sure exactly which. Well, yeah. I mean, I don't know exactly which of the 5 different types of graphs it would.
I think it's a states graph. I think you've got a states graph. I think you're going from one state of the sliding block puzzle to another.
Yes. Yes.
And so in your case here, the question of solving the puzzle is the question of finding a path from the initial condition to the final condition.
Yes. Although also maybe note, this is probably true for a lot of these different situations. I mean, the rules are kind of complicated. I mean, there's sort of a function that will determine what steps can you take, but it's like there isn't a simple symbolic way of representing sort of the, if you understand what I mean, there's a program that's required to determine what possible moves you can make.
Right, but isn't it the case? I mean, okay, so let's say puzzle solving, and here, what you're effectively saying is, it is still just a state transformation, isn't it? I mean, given a state.
Right, and solving the puzzle is just finding a path in that graph. Yeah.
Right, but there is in the multi-way graph. I mean, you could. I don't know whether you're actually using nest graph, but you probably could be. You're literally just saying, given this state, there are certain other states you can get to from that state.
Yeah, although I'm not using nest graph because it has the thing where it doesn't assume that the functions are deterministic, but yes.
Oh, that's another thing we needed to talk about, right? Oh gosh, that's right. Nest graph. Did we solve that? Does somebody know? Did we solve that problem of assuming deterministic functions in nest graph?
Or to maybe to explain, because that's a bit of a cryptic way to put it. I mean, basically the issue is that if suppose that the function you give to nest graph is deterministic, nest graph will still run it, several times. So for example, if you do the kind of trivial web crawler, right, where the function is kind of just like a URL fetch and then get a bunch of URLs, then the point is if the same website comes up twice, it'll call URL fetch on it again, which I can only assume is because, you know, it doesn't want to assume that URL fetch, or I guess now URL read or something like that is you know, deterministic. But in the vast majority of cases, it probably is deterministic. So there should at least be an option that handles that case, because otherwise, you know, the performance kind of spirals out of control.
And how does that relate to token deduplication? Isn't that the token deduplication problem? I think it's the same as token deduplication. Can anybody comment on that? Max or anybody?
Well, I think it's similar, yeah.
But wait a second.
One thing I need to point out about token duplication. So in the way we are doing it, it's not just memoization, because the deduplicated token event graphs are not only kind of conflated original token event graph, they also contain events which have tokens as inputs, which would never appear in a single state. So basically, they tell you everything that can happen, even if it doesn't happen for this specific initial condition. And you need to do that because if you want to then use the deduplicated token event graph to run the system from a different initial condition, you should be able to do that.
But you're saying it operates at the level of tokens. There's no guarantee that any given state will sample
everything
tokens.
Operates on the level of tokens.
Right, but any given state, I mean, so this was a picture here of sort of Petri net style propagation of what Petri nets would call tokens, but we have to call markers because we already have another thing called tokens. This represents a state with markers in that position, and this represents the propagation of those markers to successive states, right?
Right.
This is a particular
but the point
path.
is, in the set replace generate, I mean, in the token event graphs, the duplicate one, set branch and set replace generates, you can run this process starting from any group of tokens, not necessarily the initial state, and it will still work.
Yes, I understand. This is a complete summary of everything that can happen.
Yeah, so it's a superset
regardless of
the
whether it
conflated
actually
token event
happened.
graph.
Right. So so deduplication, the point you're making is deduplication memoizes everything, whether or not it was actually whether or not, or is the equivalent of memoizing everything, whether or not that thing actually occurred. Right? Whether or not that particular, whether or not it shouldn't really be calling or pre-caching. It's really a pre-caching of everything. Whether or not the thing occurred.
It's expanding the rules into explicit, system that you can then run in the, the same way for any system. So basically, the running a system is now a two-step process. You first generate the duplicated token event graph, also known as Petri net, and then you run that Petri net in an ordinary way, like you would, like the same way for any system.
Right. Okay, but so let's see. Okay, so again, pulling out to what we're trying to get to here. The issue is, what we want to do is have a sufficiently general formalism that all these different things we're talking about, chemical reactions, proofs, et cetera, just like, okay, big picture, we've had a fantastically successful general framework with symbolic expressions and transformations of symbolic expressions and an evaluator that goes to fixed points and things for lots of kinds of computation. What we would like to do is to expand that to new kinds of computation by having another general framework that is like our evaluator, but isn't our evaluator. And is, so the question is, what is that? What does it contain? Right? And the most minimal thing would be, I don't think it's enough to just say it's a big bag of tokens, because those tokens are knitted together into states. And those states are knitted together into foliations. And I'm trying to understand, how do we represent those things? And then when we run it, we might have something which is what we thought about previously was, if I pull up some of the previous stuff that we've thought about, and I don't know, maybe by the way, we didn't even talk about probabilistic programming here yet, which is again a very, very similar kind of issue, I think. Do you agree? I mean, do people okay, let me just see. We had made some notes previously about this. Maybe somebody
Well, tokens are knitted in the states through atoms. You don't need any extra information to create states from tokens. Except, well, you need to know how they're related to each other.
If we do it with atoms, if the tokens are knitted through atoms, but it's not obvious to me that that's the general approach, right? So are tokens always knitted into states through atoms? Okay, let me explain for people who don't know the physics lingo. Let me explain what that.
Well, atoms is anything that answers to atom Q. So it doesn't have to be like vertices in a hypergraph. Like the function names in the previous example are also atoms.
Okay, but I'm not sure. Let's take, I mean, somewhat ironically, in chemistry, it might actually be atoms or it might not be. But I mean, the basic point is the tokens are the things on which the rewrites occur. Okay, and the question is, are those tokens, how do we know how those tokens relate to each other? So in the case of hypergraphs, we're, just like, okay, how do we know if we say f of x and we say f of y and so on, we know that those two things are related because the f's are the same.
Yeah, so f is an atom in this case that connects them.
Right, but I mean, okay, I'm not convinced that this is a general enough. I mean, in other words, tokens, in the case of chemistry, we agreed up to stereochemistry and other weird things are basically collections of bonds. And it's not obvious to me that they get knitted together into compounds. Maybe they do. Maybe it is actual atoms in that case, labeled actual atoms. That's possible.
Well, I mean, if the same, I mean, sure, I mean, if it's the same atom, then yeah. I mean, you can say in cases like strings, you don't have, like, when you just write string like in the usual way, you don't have atoms in it, but you need to put atoms. So basically, in the case of strings, the atoms would be labels for string positions.
Right. I mean, we had an example.
You need them to connect the string together.
Is it just to be concrete here? I believe that the stringing. Let's see. I think there was an example here.
Yes.
So this is right. That is a string.
It's a bit an overcomplicated one because it turns it into hypergraphs, not just multi-set systems.
Okay, but this is, so what are you saying? So in this, oh, I see, because it's decorating, it's representing the A's and B's using, by having a self loop for a B and a ternary edge for it, or a non-self loop for an A. But basically the point is, this is an A1, B2, et cetera, et cetera, et cetera. In other words, it's got an index here, or more particularly, I mean, that index is an arbitrary thing, but that's the knitting of tokens into a state, basically.
Well, I mean, it's not really an index because it's not going to stay correct.
No, like I understand
once you
that.
replace
It's just an ID.
Characters. Yeah.
It's just an ID. It is an atom. It's an atom label. That so that's the way that gets knitted. And then the token, then if we say there's a rule that says BB goes to whatever, it's just statelessly looking. I just want a B and a B, and I've got these arbitrary things that are the connectors here, which I then am going to, then the transformation might turn this into an A with those two connectors, and those two connectors necessarily connect back in here. Is that a good way? Can we think of chemical reactions the same way? Is this just like a chemical reaction? Is this just like the application of a name reaction? Chemistry.
It might be. I have to think about it a little more detail. I was thinking more at the atom level, and there you don't necessarily preserve the number of hairs, as it were.
How can you not preserve it? How does it knit back in?
Well, I mean, that's what I was trying to think about is examples that might be counterexamples to having the same number of connections.
Because I believe that like in the people thinking about chemistry in terms of graphs, double push out rewriting and so on is the same kind of story. Maybe we can just ask a couple of other. Let's pick on Xerxes or James and ask about the category theory version of all of this. Can you comment on the relation to category theory, if any? Did we lose Xerxes? Maybe we lost Xerxes. Or he's saying something great, but without audio. Okay. I see that Roger joined. So we've been, Roger, I don't know, I assume you understood what we're talking about here.
Yeah, roughly.
I would like to know other cases. I mean, so we want to represent proofs, algebraic type proofs. Are there other examples? Like, for example, in the world of system modeler, are there examples of things that are essentially this type of problem? Actually, here's a question. In system modeler has two-way relationships between things, like a lever pushes on this and the thing that it pushes on pushes back on the lever and things. But as I recall, there's a version of block diagrams that is more, well, can you explain how does any of this stuff relate to system modeling?
Well, there are two things. There is at the high level, which is discrete like yours, there is something called state graph. State graph is essentially a version of Petrinets, an industrial version of Petrinets that allows you to have asynchronous updating, and it's useful for modeling things like chemical reactions, where reactions take place in parallel, and then until some event happened, you can't move on to the next event, things like that.
Okay.
Those events can be triggered, so usually you have event triggers, since you talk about Petrinets, event triggers. Those, in the case of system modeler, those events can couple directly to differential equations and continuous reactions, if you like, or continuous kinds of systems underneath. So you can imagine those Petrinets used to describe like a recipe, for a chemical factory. Mm-hmm. Heat these two, heat the fluid in these two things, then mix them, then
okay, so you're saying
raise the pressure, then do a bunch of things, but it goes on in parallel. The world is parallel, right?
Right. But the real point you're making. So I mean, I think we understand the concept of these state graphs, and we would actually call them state graphs. Bizarrely enough, exact same name, basically.
Okay. So this is state graph is a Modelica standard, and as again, this is basically still like an industrial version of what Petrinets is trying, which is sort of more an academic version of things.
I wonder whether the state graphs are exactly what we call multi-way state graphs. I think they might be.
I don't know.
But the thing you're saying is that you're hanging off those. You're hanging differential equations.
Yeah, because what those are typically used to model is sort of macro level behavior. Let's say that you have a drone, mm-hmm. and you want to sort of model, go from this waypoint to this other waypoint, do this flip, and then do this and other things. That's a very discrete set of things and actions to do, right? Yeah. But underlying that, you're going to control the different fan jets that actually, drive that drone. Those are continuous control loops. Those are differential equations. And the same thing happens in many kinds of industrial, kinds of systems, like a robot that moves around.
Okay, but so basically what that means in our setting is our events, what we're saying is just a single event. You're saying, let's break that down into something which has a continuous where you continuously go from one state to another.
Yeah, often that's I'm just saying that sort of that's kind of practice that you think of, kind of two or several levels of systems. Like you can model systems at different level of resolution. Now let's drop down to the sort of more continuous level of system modeler. System modeler is designed to model, basically things, engineering systems, and most engineering is related to physics, right? Because electrical engineering, mechanical engineering, thermal engineering, and whatnot, it relies on that we have physical models, like continuous,
right,
types of models. Now, system modeler uses differential algebraic equations. It can use differential equations, but differential equations are very limiting. So it uses differential algebraic equations, because then you can, for instance, just put all these equations together and then say, this is what I want to find out. You eliminate what needs to be eliminated. I don't want to manually do that, as you have to do with differential equations. The other thing that it uses to add richness to the world that can be modeled with those. And so one advantage of the DAE, which is called acausal modeling in this space, as opposed to causal modeling, is that they're not directed. So you can think of systems like think of a battery electrical vehicle. There you have electrical motors propulsing the car forward. But when you brake, you're doing the other way around. You use the electrical motors as generators. So you effectively run the system backwards.
Okay, but look, in terms of for example, you're saying eliminating variables. I bet that's basically the same as token deduplication.
Yeah, I mean, the way we actually do the elimination of variables is a lot of it is structural. It uses big graph reduction schemes to know structurally what can and should be eliminated trivially.
So wait. So you're basically saying your differential equations, you represent the system of equations as a graph. And
the structure of them.
Right, and so probably acausal modeling is probably an undirected graph, and causal modeling is a directed graph.
No.
Not so?
No. Not so.
How come?
No, it's just dependence. It models dependence. What depends?
So there's a triangular dependence in some sense in the causal case, or something like that.
Sort of, yes. Yeah. But that allows us to deal with things like hundreds of thousands of equations. Whereas if you actually have to deal with the formulas for hundreds of thousands of equations, you can't.
Right.
I mean, you can't really simplify.
Okay, so one thing that you're highlighting here is, in terms of methods for dealing with these systems, there are theorem proving methods. I mean, in the purely discrete case, there are theorem proving methods.
Mm-hmm.
You're saying there are algebraic elimination type methods that you could imagine using to deal with these large kinds of systems.
Yeah. So system modeler, what we call compilation of system modeler, is to transform this very relational acausal model into something that becomes causal and can actually be simulated, can be sort of, run numerical simulators on.
I understand, but if those events were just discrete events, could the formalism of system modeler still be useful? Or is the formalism solely associated with sort of actually having equations for every event?
No, I mean, this is sort of both. Okay, so what makes it sort of rich is that you need both events and continuous. So the physical world sometimes generate events. So for instance, when you press a clutch, you disengage something. It's like a discontinuous event. Or when a ball
bounces, right?
Yes, when a ball bounces, yeah. And there's a bunch of these events happening kind of in the real world. And so they have to somehow come back, and so it's not only DAEs, there's also what's called hybrid DAEs. That means that you have events and differential equations. So you can sort of, like we do in Mathematica too, like NDSolve version 9.
No, I know, I understand.
Okay. When events is that?
We're going to run out of time here, and I really wanted to, are there other people here who say, I've got a system that is also related to these kinds of things? And did Xerxes manage to connect himself, or
yes, I'm here.
Okay. Do you have comments about the sort of category theory versions of the kinds of things we're talking about?
Some of them are known to be expressed in category theory, but maybe for the others, it's not clear what type of category theory one would use. I mean, in case of Petri nets, there are a bunch of Petri nets and their generalizations, some of which are expressed in different types of monoidal categories. In our picture, one may think of using Petri nets in terms of global multiway systems with the addition of having extra objects, an extra set of rules for the tokens, as if there are two kinds of entities. One is where there are states, and on top of that, there are tokens. But I suppose in the local multiway system, Petri nets would be more natural to interpret.
But in category theory, roughly, a monoidal category is the equivalent of parallelism, in some sense.
Well, I mean, being monoidal has to do with the fact that you have a tensor product, and you can apply this. Normally, you apply this tensor product to let's say to merge states, but
Right.
then the key feature in the definition of monoidal category is that when you're trying to merge states, you should do it in such a way that it is compatible with the morphisms or the events that would have led to those states. So, for example, you have two events that lead to two states, and now you want to ask what is the event that would have led to the merger of that state. So it should be some sort of composite of the function itself, or composite of the event itself. So there should be a consistency in the way the tensor product works at the level of the functions that are generating the next state, as well as at the level of the states. So a monoidal category just gives you some consistency conditions to keep track that you're not doing something inconsistent in the way you're doing mergers.
Okay.
For us, I think what's practical about monoidal categories is that it gives a mathematical justification for how state mergers would take place in a consistent way.
But so
this reminds me of with finite state machines, when you do asynchronous products or partially synchronous products, that you do a tensor product of the states. And then you have a process that sort of filters out, what are the allowed transitions?
Is this like the wreath product business where you're taking products of machines?
Yes. But there's like a whole family of these asynchronous, synchronous products.
Right. I've never understood this, the Krohn-Rhodes decomposition theorem and all this kind of thing. Is that what this is related to?
No, that's a Krohn-Rhodes isn't that a sort of a decomposition sort of one input to the other type thing, if I remember.
Yeah, and it's usually in terms of semi-groups and simple groups.
Right.
Okay. That's a different, okay. So like, for example, if I look at a paper like this, for instance, how is this related? You've got hypergraphs in here, or is it good? You've got multi-way graphs in here.
Right.
So,
we mostly explain everything in terms of just string substitution systems, but what the statements are generic. They don't have to restrict to one particular multi-way or whatsoever. Here, of course, the main point of this was to say that we can start looking at rules in a systematic way instead of just having some initial set of rules and just put them all together and see what comes out. There's a systematic procedure for applying rules in a way that you can clearly see when paths are generated, when paths between paths are generated, when paths between paths are generated, and so on. And that can systematically be interpreted in terms of higher category theories and higher homotopies.
So what you're saying here is that in our evaluation, usually, our current evaluation model is incredibly impoverished. We just have this one path that is just, getting to an answer. Mm-hmm. You're saying, for example, the higher category business is like homotopies between evaluation paths. Like in the case of in the combinator case, for example, we could easily pick, we could say, and I don't know what it means particularly, that two different evaluation sequences for combinators, there is some homotopy between those two different evaluation paths, and there might be an obstruction to homotopic equivalence, which might be something interesting. But that's a sort of richer version of the evaluation process than we've been dealing with so far. And
right.
All right.
Right. As if there's a combinator expression between one combinator tree to another itself.
Right. Yes, but it's a but you're talking about the higher the higher categories have to do higher morphisms. So that, well, this is a is between from one proof to another proof.
Right.
And a proof is not a single combinator expression. A proof is a sequence of combinator expressions. And that's the thing we don't have a way to represent right now. And look, in our language, I mean, okay, so a key lack in our language, language design. I mean, a key thing, we have expressions, we have expressions, but we do not have a way of representing transformations do not have a way of representing the process of transformation.
Mm-hmm.
Is that a fair statement, guys? I mean, so in other words, we can say, like in the proof, when we give that in a proof object, it's a big mess how we say where a pattern applies. Where does a pattern apply, for example, which is otherwise known as, AKA, how does a state decompose into tokens? Isn't that right? So in other words, when we say we are applying a rule, like in that to wherever it was up here, this is saying, where does it apply? Oh, it's wherever it is. I don't even know where it says. Sub-pattern, I don't even know where it says where it applies. But it has to give a part number for where this rule applies to this thing, if I'm not mistaken.
Mm-hmm.
And that's a very yucky thing, which I don't think we have a good way to do. Anybody want to comment on that?
I have to go in a minute, but I'll just say that Xerxes, I don't know if you've looked into this, but there are these kind of categories called Tanakian categories that Deline and Milne have studied, which are basically monoidal categories, but they include some additional structure that makes them amenable to, transformation representations. And so maybe we should discuss this at some point, because if we're interested in monoidal categories, but we have this transformation representation problem, this might be a lead.
Yeah. But here, these Tanakian categories and others, those are, of course, special cases of categories that were built for these operations that you're mentioning. But this kind of this framework rather of this higher category theory is a generic framework that encompasses that and many other such examples. Here, I was just giving a generic example of how higher categories gives you the mathematical formalism to capture abstract homotopies, and those were useful for us to build these higher multiways with higher order rules.
Okay, let's. Okay, anybody else got comments on any other analogies? And then I want to just look at a few things from our live stream, and then unfortunately we have to wrap up, even though this is, I consider this rather interesting. Any other comments from people about other analogies we haven't talked about, and so on? I noticed a reference from our live stream from Richard about stochastic logic programming. Okay, that's something we should look up. I have not. I guess stochastic logic programming is the obvious kind of probabilistic programming approach to logic programming. And I don't know how this all relates. I mean, certainly in like quantitative finance and other places, there are endless Monte Carlo simulations of processes that presumably are closely related to what we're talking about here. Anybody want to comment on that? Roger, do you have any comments on that?
Sorry, could you say that again? The last
I'm saying that in things like quantitative finance, you are deriving, one of the outputs, okay, possible outputs, right? Possible outputs. They're things like, add up every leaf, which is e.g. recursive function evaluation. Okay, another thing is find a winning path. That's search, logic programming, etc. etc. Another is find a probability distribution over paths, which I claim, or something like that. That's like Monte Carlo and things like this, right?
Mm-hmm.
And that's like probabilistic programming, I guess. Is that a correct statement?
I think so, yeah. I was thinking like there's something I saw used in economics and metabolism, which reminded me of what Roger was talking about, which is called the von Neumann's model, where you have a bunch of, little factories that consume inputs and produce outputs. And you basically want to know like what things are crucial, that if you turn off some faucet, the whole system halts, what aren't, because they can be synthesized otherwise, and so on.
Yeah, that's interesting. So that's a different case where you're saying, yeah, I don't even understand. I mean, again, the whole point is at the bottom of it is some giant multi-way graph. We are sampling different pieces of that multi-way graph. And I claim these different forms of computation, just like our current model of computation is input, crunch, 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 output. That's our model of computation. I claim here there are multiple kinds of ways that we have to probe essentially the computation object that we're getting out. Okay, there's a question, there's a few comments on our live stream. There are complaints about our theorem prover, which I think are a little bit, I think our find equational proof is a pretty strong theorem prover as equational theorem provers go. And it's a different thing to do proof assistance is different. And okay, that's another kind of thing, is the proof assistant output. It's not really an output. But another thing will be a proof assistant, which is a kind of a human assisted path finding. In other words, the framework that we've got here should also allow a proof assistant where you are, human assisted, doing the path finding in a human assisted way, right? Let's see. Richard is saying edges can represent axiom A is used in deriving T, but also theorem T depends on axiom A. Is actually unprovable, right? Okay, yes. Let's see. Richard is commenting, stereochemistry can be supported when you have conditional rewrite rules depending on attributes. Okay, I can believe that.
It's being what, geometry or something like that?
Well, I assume that this is some attributed, where it isn't just the state, where you're carrying information other than just the state. That's what you have to do. I mean, you have to carry some metadata that isn't just the local state in order to say how that glues into the rest of the molecule.
Yeah, at the very least, it would be an ordering, if not 3D geometry.
Right. Richard is commenting on Robinson's unification algorithm, which I do not know, and I'm going to paste in what he wrote here because I don't know it. Somewhere here I talked about unification. I don't know where it was.
It's a standard theorem proving, algorithm.
Right, but how does this? I mean, so okay, so this is right. But this is something very much like a sort of law of inference type thing, is it not? I think so. I think that's that's what we're referring to generically as laws of inference, I think. Okay, let's see. Richard is commenting, common sub-expression elimination. That seems like an interesting comment, but I don't fully understand it. Okay, Rich is commenting, when he implemented 3D visualization of our physics, of a basic version of our physics project, just unify the rules with the graphs and then apply deletion and gluing operations. Yes, I agree. I mean, you can do graph rewriting with deletion and gluing. And the double push out is the algebraic version of that. Yes, I agree. Okay, so Richard has suggested a number of very interesting people that we contacted before. So I take his suggestions very seriously here, suggesting a certain Stephen Muggleton, symbolic form of machine learning. Okay. Oh, that's interesting. Okay, well, I think we just have to look this up. And Dan is asking about the theorem prover. Is there a hands-on tutorial? I hope there is. I mean, I think if you look up find equational proof, I think it has fairly extensive discussion. All right, I think. Oh gosh, we're. I think I have to go because I'm really late for something here. But and Roger's just sending over a state. Oh, the pointer to the state graph. Oh, I see. Okay. That's very explicit. I mean, that's literally very Petri net-ish here.
Yes.
Isn't it lovely that there's so much unification that we can do? I don't know. I think this is pretty interesting. I don't know what other people think, but I think this is I think we're at a moment where if we do this right, we can really unify a huge number of things. It's just the more unification, the more difficult it is. But and the problem is to not end up.
I think that the very simple thing, we have compound expression means that expression 1 is sequentially after before. Well, why don't we have concurrent expression that says it doesn't give an explicit ordering?
Yeah, I know. So I was thinking about a thing called multi, which is exactly that.
Yeah, it needs to be kind of easy to do, kind of like vertical, like or. Instead of semicolon.
But you see, that isn't enough, Roger, because the difficulty is, the real difficulty is, the thing we take for granted, which is the evaluation process, we have to represent that symbolically.
Yeah, we have to. Yeah, but I'm tired of hearing this, the evaluator can't do this, can't do that. Like, what the fuck? Rewrite it. We've rewritten everything else in the system. Let's fix the evaluator.
But that's not the point, though, Roger. The point here is that we need a different kind of evaluator. Right. I mean, the question of whether the evaluator can.
But let's say that it can't be multi-threaded because of memory management in the evaluator. Okay,
no,
let's fix it.
Silly. Yeah, right. That's silly, but that's not my point. My point is that the difficulty.
But we need to also have the authoring. Okay, one also needs to if the author has done with sequential promise in the code, it's very hard to sort of excavate parallelism.
Back in SMP, back in 1979, I used to have an attribute for functions that said whether their arguments could in principle be evaluated not sequentially. Needless to say, while that was in principle tagged in the code, it was never implemented.
No, but I could see, instead of using semicolon between statements, I can use, a vertical bar.
Or something. Yes, but that's not good enough. The problem is what we're realizing is, and this is the whole story of a lot of what's coming out in the physics project and so on. The actual representation of the process of evaluation is important. It's not good enough. All these multi-way graphs that we're drawing, which actually matter what those graphs are, those are representations of the process of evaluation, which happens to be a trivial chain in the case of our current evaluator, but we need a representation of that. And that's something which, like in mathematical proofs, for example, there are usually sort of laws of inference, which are the implicit thing, which you do not represent. You just say this and this and this follow from this and this. And you're not sort of, I don't know what I'm trying to say. There's in our system, the evaluator is it just does what it does. You're not representing the process by which it does it. That's what I tried to do with trace long ago. Not a success. But trace was an attempt, if we say, trace of 1 + 1 + 1, for example, that was not very interesting. But I don't know what a good example is. 1 + 2 × 2 + 3, something like this. Okay, whatever. This is attempting to show evaluation chains. It doesn't do a good job. We've never succeeded in making that work. But I'm saying now what we have to do is symbolicize the process of evaluation. And I really need to go because I'm super late for something. but this was very interesting, guys, and I look forward to continuing it. And if people have, we will get a mailing list going internally for this process and project, and yeah, to be continued. All right, I have to run. Thanks, and thanks to comments on the live stream. Oh, Richard has another interesting comment here. All right, we have to read these separately. Great. Okay. Bye, everyone. Thanks.